In the previous lectures, we have been studying about scheduling algorithms, and we have discussed many scheduling algorithms. So in this lecture, we will be solving some problems related to the scheduling algorithms that we have discussed. So if you have watched all those lectures, then with the knowledge that you have gained from those lectures, you should be able to solve these problems without any difficulties. So these problems that we are going to discuss here are taken from GATE CSE paper, which have been asked in the previous years. Alright, so let's see what are these problems, starting from the first one. So here is our first question. Consider a set of n tasks with known runtimes R1, R2 up to Rn to be run on a uniprocessor machine. Which of the following processor scheduling algorithms will result in maximum throughput? And we have four options. Option A, round robin. Option B, shortest job first. Option C, highest response ratio next. And option D, first come, first serve. So this question is from GATE 2001 CS paper. Alright, so let's try to understand what this question says. So here we are given a set of n tasks with runtimes R1, R2 up to Rn respectively, and they are to be run on a uniprocessor machine. So the question is asking us which of the following scheduling algorithms will result in the maximum throughput. So what do we mean by throughput? So throughput here refers to the number of processes that are executed per unit time. So it is asking us with which of the scheduling algorithms will we get the maximum number of processes executed. So let's see. Let us try to recall these algorithms that we have studied and try to figure out what the answer will be. So first of all, we have the round robin as option A. So if we are using a round robin scheduling, we know that in round robin scheduling, there is a quantum of time defined and each process will be allowed to execute for that particular time quantum, and then that process will be preempted and given to the next process. So we see that there is somewhat a fixed number of processes that will be executed per unit time. It is not actually fixed, it will depend upon the burst time of the processes, but on an average, it will depend upon the time quantum that is defined in round robin scheduling. Now, the next one is shortest job first. In the shortest job first scheduling, the shortest process or the process having the shortest burst time will be the first one to get the CPU for its execution. And then after it is done, the next shortest process will be the next one to get the CPU. So it goes on like that. So here we see that the process with the shortest burst time comes and gets the CPU and finishes it quickly, and then the next shortest one gets it, finishes it quickly, and then it continues like this. Here we see that there could be many processes executed per unit time. Alright, so this looks like the answer, but let's analyze the other options as well. So option C is highest response ratio next. So we have not discussed about this algorithm as such, but from the name itself, it is easy to understand that the process having the highest response time will be the first to get the CPU. Or when processes are executing and waiting in the queue, the next process to get the CPU will be the one with the highest response ratio. So even here we see that it will depend upon the response ratio of the processes. So if we compare it with the shortest job first, we can easily say that the shortest job first will be the one which will be allowing more processes to be executed. And then the option D that we have is first come first serve. So definitely we know that first come first serve will not be the algorithm which will give the maximum throughput, because the first process that arrives will be executed, and even if it's a very long process, it will first be completed and only then the next processes will get the CPU. So it is definitely not first come first serve. And we see that it was not highest response ratio next as compared to shortest job first. And round robin also we saw that it depends upon the quantum of time. So among these four options, shortest job first will be the algorithm that will give the maximum throughput, because in this algorithm, the shortest job is given the CPU, it executes and it goes out, and the next shortest job comes and it executes and it goes out, and this process happens very quickly. So shortest job first will be the algorithm among all this which will be giving the maximum throughput. Alright, now let's go to the second question. So here is the next question. Which of the following scheduling algorithms is non-preemptive? And we have four options. Option A, round robin. Option B, first in first out. Option C, multi-level queue scheduling. And option D, multi-level queue scheduling with feedback. So this question was asked in GATE 2002 CS paper. So the question is asking us, among these four scheduling algorithms, which is non-preemptive? So what do we mean by preemptive and non-preemptive? We have already studied this. Preemptive is when a process is executing if it can be interrupted and the CPU can be taken away from it and given to another process before it completes its execution. That is what we mean by preemption. And non-preemptive means that thing is not allowed. So let's analyze these options again one by one. Round robin. So we know that in round robin there is a particular quantum of time defined and each process will be allowed to execute for that quantum of time. So if there are 3 processes, the first process will get the quantum of time and it will be executing, and if it has not completed its execution within the time quantum, then the next process will be given the CPU once the time quantum expires. So we see that there is preemption here because that first process which was executing, even though it has not completed, the CPU is taken away from it and it is given to the next process. So clearly there is preemption in round robin scheduling. And the next one is first in first out. So this is just another way of saying first come first serve scheduling. So don't get confused, it just means the same thing. So in first come first serve scheduling that we have discussed, we have seen that when the processes arrive in the ready queue, the first process that arrives will be the first to get the CPU and it will complete its execution, and only after that the next process will get the CPU and then that will complete its execution and then it goes on for the other processes waiting in the queue. So here we see that only when one process has completed its execution fully, only then the next process is given the chance. So there is no preemption happening here. So we can be clear and sure that first in first out or first come first serve is the algorithm which is non-preemptive. So we are quite sure about this option. So even if you don't look at the other options, it's fine because there will be only one right answer. But let's just give a look. We see that option C is multi-level queue scheduling, where we know that there are different scheduling algorithms that can be applied, so preemption will be there. And even in multi-level queue scheduling with feedback, even in this also there are different scheduling algorithms that can be followed, in which some may be having preemption. So definitely there is preemption in these two algorithms. So the answer for this question is option B, first in first out. Alright, so let's go to the next question. So the next question is, which of the following statements are true? So we are given 3 statements and we have to figure out which of them are true. So let's see. Statement number 1 is, shortest remaining time first scheduling may cause starvation. Number 2, preemptive scheduling may cause starvation. Number 3, round robin is better than FCFS in terms of response time. So we have 4 options. Option A says that 1 only. That means only the first statement is true. Option B says that statements 1 and 3 only are true. Option C states that statements 2 and 3 are the only ones that is true. And option D states that statements 1, 2 and 3 all are true. So this question was asked in GATE 2010 CS paper. So let's try to analyze these statements one by one. So the first statement says, shortest remaining time for scheduling may cause starvation. So what is starvation? Starvation is when a process is waiting to get the CPU, but it ends up not getting the CPU and ends up waiting for a very long time. So that is what we mean by starvation. So in shortest remaining time for scheduling, we know that the process with the shortest remaining time will be the one to get the CPU next in the queue. So let's say that there are processes waiting in the queue and there is a process that is longer than all the other processes that are currently there. So they are all waiting, and the process having the shortest remaining time gets the CPU for its execution, and after it completes, the next one gets. And let's say that the last process which is there, which was having the longest remaining time among them, finally was going to get the chance to execute. But just at that time, another process arrives which is having a shorter remaining time than this one. Then what will happen? That process will be getting the CPU, the one which just arrived having the shorter remaining time than the one we are talking about. So that other process did not get the CPU. And we also know that the shortest remaining time for scheduling can also be preemptive. So let's say that when that process finally got its chance for execution and it was executing, and again another process arrives which is of shorter time than the one that is executing, then what will happen? The process that was executing will be preempted, and then the one that arrived now will be given the CPU. So we see that that process could end up waiting for a very long time and cause starvation. So shortest remaining time for scheduling may cause starvation. That is true. Then second one says that preemptive scheduling may cause starvation. So preemptive scheduling is when the process that is currently executing can be preempted. That means the CPU can be taken away from it and given to some other process. So this is also true because in this case, I have just explained how preemption works, and when preemption works, how the starvation can occur. So preemption can be there in different scheduling algorithms. So when preemption is there also, there is a possibility of starvation. So statement number 2 is also true. Now let's see the third statement. Round robin is better than FCFS in terms of response time. So when we have discussed round robin, we have seen that it is the best algorithm for time sharing systems, and definitely even from the problems, we have seen that round robin is having the better response time. Because in FCFS, the process that comes first will be the first to get the CPU when that pattern is followed. And if the process that is executing is of a very long burst time, then it will end up using the CPU for a very long time, and there is no preemption that will happen in FCFS. So the response time will be less in case of FCFS. So round robin is definitely better than FCFS. We have seen that when we have also discussed the lectures. So we have seen that statement 1 is true, 2 is true, 3 is also true. So all of them are true. So which options says that all of them are true? Option D. So the answer is option D. Alright, now let's see the next question. So here in the next question, it says, consider the 3 processes P1, P2 and P3 as shown in the table. So we have 3 processes with process IDs P1, P2, P3 and with arrival times 0, 1, 3, and the time units required, that is like the CPU burst time, are 5, 7 and 4 units of time for P1, P2 and P3 respectively. So here it says, the completion order of the 3 processes under the policies FCFS and RR2, which is round robin scheduling with CPU quantum of 2 time units are, and we have 4 options. So what they mean by this is that if these processes are following FCFS, which is first come first serve scheduling, and also if they are following round robin scheduling with a time quantum of 2 units, what will be the completion times of P1, P2 and P3? So we have 4 options. In option A, it says if it is following FCFS, the completion order will be P1, P2, P3, and in round robin, the completion order will be P1, P2, P3 as well. And in option B, it says in FCFS, this will be the order, and in round robin, this is the order. And option C and D also are telling us some values like that. So we want to see the completion order, that means which is completed first in each of these algorithms. So let's try to analyze these options and find out which will be the correct option. So since there are 4 options, and instead of wasting our time analyzing all of them, we can use some technique. So let's see. We know that in first come first serve, the first process that comes will be the first one to get the CPU, and only after it completes, the next will get the CPU. So this method is going to be followed in FCFS, that's for sure. So we know that in FCFS, the completion order will be P1, P2, P3. P1 is the first one to arrive at time 0. So this will be the first to get the CPU, and how much ever time is required, it will take without any preemption, and it will complete. Then the next one to arrive is P2 at time 1. So P2 will be the next to get the CPU, and then after it completes, P3 will get the CPU that arrives at time 3. So P1, P2, P3 will be the order for FCFS for sure. So let's see in which among these options are we having the order P1, P2, P3 for FCFS. So we see that in option A, FCFS has P1, P2, P3. So option A could be one possibility. And option B, here we see it is P1, P3, P2. So option B is out of the picture, no need to discuss. And option C says again P1, P2, P3. So this is also another possibility. And option D says P1, P3, P2. So this is not going to be possible for FCFS. So option D is also out of the picture. So our possibilities are between option A and option C. Alright, now let's see in round robin which will be the first one to complete and what will be the completion order. Alright, so in round robin, here we are given that the time quantum is 2 units. So each process will be allowed to execute for a time quantum of 2 units. So if we are following a round robin scheduling with a time quantum of 2 units, let's see how will these processes be scheduled. So we see that process P1 is the first one to arrive at time 0. So P1 will be getting the CPU for its execution, and it will be executing for a time quantum of 2 units. So when P1 is executing, at time 1 P2 has arrived. So P2 will be waiting at the queue. So let us just make the queue here so that we will be able to remember it. So let's say this is our queue and P2 is waiting at the queue. So P1 will execute for 2 units of time, and after that it will be preempted and it will go to the tail of the queue, and P2 will be getting the CPU. Now when P1 was preempted, what is the remaining burst time of P1? The remaining burst time of P1 is 3 units of time because it has executed for 2 and it is preempted, so it comes at the queue now. And then P2 went from the queue and is now using the CPU. At that time, even P3 arrives. So P3 arrives and it is waiting at the tail of the queue. So P3 is at the tail of the queue and P2 will execute for 2 units of time. So after 2 units, P2 will be preempted. So after 2 units of time, the remaining burst time of P2 will be 5 units. And then P2 will be put at the tail of the queue, preempted and put at the tail of the queue. And the next process will be given the CPU. What is the next process? It is P1. So P2 comes at the tail of the queue and P1, which was at the head of the queue, now again got the CPU for its execution. And P1 will again be allowed to execute for 2 units of time. So after the 2 units of time, what is the remaining burst time? The remaining burst time is 1 unit. And after that, P1 is preempted and it is also put at the tail of the queue. And the next process in the queue will get the CPU, which is the next process, that is P3 at the head of the queue. So this will be the process to now get the CPU for execution. So it is removed from the queue and it gets the CPU, and P3 also will execute for 2 units of time, and after that it will be preempted. So P3 is preempted and put at the tail of the queue, and the next process will get the CPU, which is the next process, P2. P2 is at the head of the queue. This will get the CPU. Now P2 will get the CPU and will do its execution, and P2 executes for 2 units of time, and after which it will be preempted again. So when it is preempted, it will be put at the tail of the queue here, and then P1 will be the next to get the CPU. So if you see here, P1 will get the CPU and then it is having only 1 unit of time that is remaining. So within the 2 unit of time that is assigned to it, it will complete its execution. So P1 will finish its execution. So P1 is the first one to finish execution. So we see that in both of these options, P1 are there as the first one. So P1 is going to be the first, we know it. And we also see that P3 is having a remaining burst time of 2 units of time and P2 is having a remaining burst time of 3 units of time. So we don't have to draw the queue and do this calculation again. If we just see it, we can analyze and understand that the next time if P2 gets the CPU, it will only execute for 2 units and again it will have a remaining of 1. But when P3 will get, it will complete its execution within the 2 units of time because it is having only 2 units. So P3 will definitely be the next one to complete, and after that P2. So the order will be P1, P3, P2. So which of these options has P1, P3, P2? Here, option C has P1, P3, P2. While in option A, it is P1, P2, P3. So option C is definitely the answer for this question. Alright, so now let's go to the next one. So here is the next question. A scheduling algorithm assigns priority proportional to the waiting time of a process. Every process starts with priority 0, which is the lowest priority. The scheduler re-evaluates the process priorities every t time units and decides the next process to schedule. Which of the following is true if the processes have no input-output operations and all arrive at time 0? And we have 4 options. So before we go to the options, let us try to understand what this question means. And this was asked in GATE 2013 CS paper. Alright, so the question says, there is a scheduling algorithm which assigns priority proportional to the waiting time of a process. So it is based on priority and the priority is proportional to the waiting time of a process. That means more the waiting time, higher the priority. It is proportional. So the processes having more waiting time will be having higher priority. And every process starts with a priority of 0, which is the lowest priority. So for the starting, every process will be starting with 0 priority, which is the lowest priority. And then the scheduler will re-evaluate the process priorities every t time units and decide the next process to schedule. So after every t time units, the scheduler will re-evaluate and decide the next process to schedule. It will re-evaluate the priorities after every t time units. So keep this in mind. This is very important. So it says which of the following is true if the processes have no IO operations and all arrive at time 0. So if they all arrive at time 0 and if it has no other operations like IO operations, which of the following statements are true? So option A says this algorithm is equivalent to the first come first serve algorithm. Option B, this algorithm is equivalent to the round robin algorithm. Option C, this algorithm is equivalent to the shortest job first algorithm. And option D says this algorithm is equal to the shortest remaining time first algorithm. So we have 4 algorithms given here first come first serve, round robin, shortest job first, and shortest remaining time first algorithms. So if the scheduling algorithm is following this kind of a method, then to which of these 4 algorithms do this method resemble, or is it same? So here when we were discussing this question, I told you that there is a T time units. So even though there is a priority proportional to the waiting time of the process, we see that every process's priority will be re-evaluated after T time units, and then the next process to schedule will be decided at that time. So which of the scheduling algorithms here looks like this? So it is definitely not first come first serve, and it is also not the shortest job first or the shortest remaining time first. I told you this is the important part, T time units. So whatever is done after every T time units, the priorities are going to be re-evaluated. So it is like the round robin scheduling algorithm. So in round robin, we are having a time quantum. So here what is happening in this method that is given here, after every T time units, there is a re-evaluation happening, and then the next will be decided. So here also there is something of like a time quantum, T time. So after every T time, the next process is decided. So it is clear that this algorithm is equivalent to the round robin scheduling algorithm. So the correct option for this question is option B. Alright, so these were some problems related to the scheduling algorithms that we have discussed, which were asked in previous year GATE CSE papers. So if you are thorough with these algorithms, and if you understand how it works, and if you practice solving those problems that we have solved, then this kind of questions can be easily answered by you. And when there are this kind of problems, just take some time to understand how it is working, and you will be able to easily figure out the answer. So I hope these problems about scheduling algorithms were clear to you. Thank you for watching, and see you in the next one.